Today we shall start calculus of variation. It is a very powerful technique which is extensively used in modern physics. This calculus of variation deals with the extremization of certain integrals called functionality. Before we shall come to it afterwards, let me first explain what we mean by extremization problem. If we have a function y which is a function of x, then extremization of y means finding out its either maximum or minimum value. Sometimes the value may be a point of inflection also. In ordinary calculus, what we do, we have y as a function of x, and then we find for extremization we set dy dx, and we can set it to be 0. This is for extremization. And if with this, secondly we calculate d2y dx2. If this is greater than 0, then we get minima. If it is less than 0, we get maxima. And if it happens to be 0, we get point of inflection. As for example, we find out the critical constant of a real gas by differentiating twice and setting the second derivative value to 0. This is the technique that we generally use in extremization problem in calculus, ordinary calculus. But in calculus of variation, the problem is something different. In calculus of variation, we have an integral. We have an definite integral. Say we know the integration x1 to x2, some function of y prime, that is del y del x and x, and this is where we have used y as a function of y is a function of x, and y prime is dy dx. So it is a function. F is a function which depends on y, its first derivative, and the independent variable x. In fact, x is the independent variable and y prime are dependent variable. To distinguish between dependent and independent variable, we have to put semicolon between these sets, and this value is j, the integral value is j, and it depends on the particular choice of y. As for example, say this is an xy plane, we are performing the integration. This is point 1 and this is point 2, and we say we move from point 1 to point 2. We can move from point 1 to point 2 in a variety of paths. There are infinite number of paths which connects point 1 and 2. For each of the paths, y has different form. As for example, here y is related to x by a straight line relation, and in this case the relation is non-linear. So each of the paths connecting 1 and 2 has different functional difference. That is, y is different for each of the paths. Here in calculus of variation, we try to find out the value of y for which this integral has an extremum value. So here the problem is different. In ordinary calculus, we know y, and from knowing the value of y, that is the functional dependence of y on x is known, and then we differentiate it once or twice to get the information about the point extremum point. And here the problem is different. We want to extremize the integral on the right hand side. The value of this integral crucially depends on function on y. So we have written j, the integral, definite integral has been denoted by j, which is a function of x, a function of y, where y is a function of x. So in fact, j is a function of a function. It is called a functional, unlike f. F is a function, y is a function because y, we know how y is related to x. Here the value of j, depends on y as well as on x. So in other words, we call it a function of function, and it's called a functional. Our objective is to choose that particular path for which the integration has an extremum value. By extremum value, we mean the value may be a minimum one or maybe a maximum one. But in preliminary stage of calculation variation, we shall restrict ourselves to the extremization problem, that is, we shall calculate first derivative and set it to 0, and we cannot say definitely from this calculus point of view whether this corresponds to a minimum value or maximum value. That needs to go for second order derivative, which in calculus of variation is not very easy. So the question of maxima or minima will be determined by our experience. Nonetheless, the first order theory gives us plenty of information regarding mathematical and physical problems. As for example, since our childhood we have learned that the shortest distance between 2 points lying in an Euclidean plane is a straight line. But we never proved this. We have just memorized the statement. The calculus of variation allows us to prove that the minimum distance between 2 points on a plane is indeed a straight line. So our aim is to find out y which extremizes the integration. So for example, we again consider the 3D picture. This is y plane, this is x axis, this is point 1 and point 2, and 1 point and point 2. Say this green color part is the exact part for which the integral is an extremum 1, and we have some other parts. There are, as we have already said, there are different paths connecting the same terminal points, and for each path y is different from the exact one. So the one way of stating this problem is that a variation of j of y of x is equal to variation of this integral x1 to x2 f of y prime x dx is 0. As we have done, and for ordinary calculus, for extremization problem, first derivative is put to 0. This is the variation is set to 0. We distinguish, we say that this is the exact path and the other neighboring paths differs from the exact path by a parameter. So to say, we define this is exact path y of x, let y of x is equal to y of x0 is the exact path. This is the path that we intend to find out, and we define a varied path as capital Y of x. We define a varied path by capital Y of x is equal to small y of x times alpha, which we say that y of x0 plus alpha times eta of x. That means for this path at a particular point of x, the value of y on this varied path, this is a varied path. On this varied path, this is the value of capital Y. The value of y is capital Y, and the value of x, y for exact path is this. So this path is the departure. So if we take, this is the x value, this much is capital Y, this much is small y, and this is alpha eta of x. This is the variation. So this is the variation from the exact path. One more thing, that all the curves has the same endpoints. So y at x1 is equal to y of x1 0. This gives you eta of x1 is equal to 0. So is for the other terminal point. So we conclude that with eta at x1 is equal to 0 is equal to eta at x2. Eta at x1 is equal to 0 is equal to eta at x2. So there is no variation of y at the extreme points. Now to find out this condition, we say that we differentiate or we first define the integral, this integral j of y of x, y of capital Y of x and alpha. This depends on j, and which we define as integration from x1 to x2 f of capital Y prime and x dx. This is the value of the integral j, which depends on y as well as on alpha, and if we set alpha is equal to 0, we get the exact part. Now to the extremization problem is, we say that dj d alpha at alpha is equal to 0 is 0. This is the extremization condition. This is the condition for extremization. This is same thing as we have done in ordinary calculus. for extremization we calculate the first derivative and set it to 0. Here we have differentiated with respect to the parameter alpha, and we have argued that for the right path or the exact path, alpha has to be 0. So first let us calculate what we know. We first calculate what is dj d alpha. This is d alpha of integration from x1 to x2 f of y prime of x and dx. If we take the differentiation within this we get that dx. Here we have used the chain rule. Chain rule means we are differentiating alpha. This quantity, this integrated quantity over with respect to alpha. And there are y which depends on alpha and y prime also depends on alpha. But the independent variable x do not have any alpha dependence, so there is no alpha part, no x part is there. We first try to find out this quantity. If we consider the second part, keep the first part unchanged, so we have x1 to x2 let me first calculate the derivatives. You see that y of x is equal to small y of x0 plus alpha beta of x. So del y del alpha is equal to eta of x, because y of x0 doesn't have any alpha dependence, and if we differentiate it first, y prime is equal to del x, then this is y prime at x0 plus alpha eta prime of x, and so we have del y prime del alpha is equal to eta prime of x. So we substitute these two values over here. So this is del of capital Y. Then for del y del alpha, it is eta of x plus del f del y capital Y prime, and for del y del prime is eta prime of x dx. Then we integrate the second term by parts. So the first term remains intact. The first term is x1 to x2 del f del capital Y eta of x. For second term, firstly we consider this is the first function and this is the second function. So first function unchanged, del f del y prime, integration of the second. So integration of the second is eta of x and it is calculated at x1 and x2. This quantity is finite and eta at x1 is equal to 0 and eta at x2 is 0. So this part is 0. And the second part term is integration from x1 to x2. So dx of del f del y prime times theta of x dx. I hope this part is readable. Let me check. Yes. So this is the value of integration. So we have, let me again explain. We integrated this term by parts. So first, this is the first function. So this function unchanged. Integration of the second. So integration of eta prime is eta, and in the both limits x1 and x2, eta is 0. So this quantity is 0, provided the left and right prime is fine. The second term minus derivative of the first. This is the dx of del y prime time integration of this. Integration of second function integrated over there. So the result, total result is x1 to x2 del f del y. This is, here is eta, here is also eta, minus dx of del f del y prime eta of x dx. This is the value of dj d alpha. Now we come to the condition that this is equal to 0 at alpha is equal to 0. If we set alpha is equal to 0, then capital Y reduces to small y, and capital Y prime reduces to small y prime. So let me write these things once again for the condition is that dj d alpha dj d alpha is equal to integration from x1 to x2 del f del y minus ddx of del f del y prime eta of x dx. When we said that dj alpha at alpha is equal to 0 is equal to 0, so we get integration from 1 to 2. This is del f del small y, not capital Y, minus ddx of del f del y prime, not capital Y, because alpha is 0, eta x dx. Since this quantity is 0, the integrand is 0, which says that del f del y minus dx of del f del y prime is equal to 0 is the condition. So we started with the problem. We started the problem as we know this one f functional form of y. We know the dependence of f on y, y prime and x, but we do not know how y depends on x. And we say that for the actual part, this integral will have an extremum value and y will have that particular or proper value or right value. To distinguish between the actual path and varied path, we introduced a parametric dependence of y on a parameter alpha, and we define capital Y, which is an alpha dependent path. And this variation of the varied path from the actual one is signified by this quantity alpha eta x, and since the endpoints are same for all the paths, eta must be same must be 0 at the endpoints. That is, this is the condition. We then recast the problem of extremization as that we differentiate this value alpha dependent functional with respect to alpha and set it to 0 at alpha is equal to 0. So as we are habituated of doing parametric differentiation, we are ultimately through mathematical steps come to this problem, this part, and when we set alpha is equal to 0, capital Y reduces to small y and capital Y prime reduces to small y prime. So this is the condition for extremization of the integer functional J. And obviously, if this has to be 0, then the quantity within second bracket is has to be 0, and this is known as Euler-Lagrange equation. For problems of physics and mathematics, we generally know the functional form of f, and once we know the functional form of f, we get a differential equation for y from this, and which can be solved to get y as a function of x. Before going further, let me consider a few special cases, and then we shall use this technique to calculate few very simple cases. Firstly, so we have obtained the Euler-Lagrange equation. That is, the extremization problem is reduced to, so del J is equal to 0 is integration 1 to x1 to x2 f of y prime x dx. This is equivalent to writing of this differential equation. This is Euler-Lagrange equation, or first Euler-Lagrange equation. You see that if f doesn't have any explicit dependence on y, as for example, if you consider the path connecting the distance of path connecting point 1 and 2, one two-dimension, the path length ds is governed by dx square plus dy square. So we write ds is equal to 1 plus y prime square to the power half dx. And if we want to find out the shortest path, then this f is governed by this path. So our problem would be to extremize the path 1 to 2 is actually becomes x1 to x2 1 plus y prime square to the power half dx. So here the functional is f of y prime x is actually depends. Here we see that f doesn't have any y dependence, so del f del y is 0. So case 1, if del f del y is equal to 0, that is y f doesn't have any explicit dependence on y, then we have dx of del f del y prime is equal to 0. Del f del y prime is equal to 0, which indicates del f del y prime is equal to some constant. Now let me calculate del f del y prime in this case. Del f del y prime is equal to of 1 plus y prime squared to the power minus of 2y prime. So this is equal to y prime divided by y prime squared. So for this problem, we see that extremization problem or Euler-Lagrange equation gives us that y prime plus 1 upon y prime squared is some constant c1. On squaring, we get y prime squared is equal to c1 squared 1 plus y prime squared, or minus c1 squared y prime squared is equal to c1 squared, or y prime squared is equal to c1 squared 1 minus c1 squared, say c2 squared. This gives you y prime is equal to dy dx is equal to c2, or y is equal to c2x plus c3, which is the straight line. So the calculus of variation is so powerful technique which very easily establishes the fact that the shortest distance between 2 points on a plane is a straight line, which we could not prove earlier. Earlier, what we said, what we did, we assume the fact, but the calculus of variation allows us to find it very easily. This is one form, one very special form when f does not depend explicitly on y. Indeed, f has implicit dependence. Even in this case, f has implicit dependence on y through dy dx. We now consider another special case when the functional f doesn't have any x dependence. That is del f del x due. Then what happens? We calculate d of dx. This is f is a function of x, y, and y prime. So we have del f del x plus del f del y del x plus del f del y prime y double prime. And we also calculate this part dx of y prime del f del y prime. So this is y double prime del f del y prime plus dx of y prime dx of del f del y prime. You see that these two terms are same, So if we calculate this, this may not be very prominent impression, so let me write it once again. dx of f minus y prime del f del y prime. That is, we take the difference of these two equations. We see that this term cancels with this, and we have del f del x plus del f del y prime, and for this term we have minus y prime dx of del f del y prime. This can be written as del f del x plus, taking y prime common, del f del y minus dx of del f del y prime. As for this Euler-Lagrange equation, this is 0. So we have del f del x. If del f del x is 0, if del f del x is 0, then we have this part is 0, that means f minus y prime del f del y prime is equal to 0. This is another some special case of Euler-Lagrange equation, or sometimes called Euler-Lagrange equation 2. So we have obtained two different versions of Euler-Lagrange equation. One is this form, and another alternative form of it is dx of f y prime del f del x is equal to del f del y prime is equal to del f del x. This is Euler-Lagrange equation 1, Euler-Lagrange equation 1, then it is called Euler-Lagrange equation 2, and there are yet another version of Euler-Lagrange equation. I am going to establish the third version or third Euler-Lagrange equation. Now, dx of del f del y prime. This can be written, dx operator can be written as del x plus del y, using chain rule, y prime del y plus y double prime del y prime operating on del f del y prime. So we get del 2f del x del y prime plus del 2 if we use this value for this part, then the Euler-Lagrange equation gives dx of del f del y prime is equal to del f del y gives us del f del x del y prime plus third version of Euler-Lagrange equation. So there are three different versions of Euler-Lagrange equation. With this theory, we end this first lecture, and in the second class we shall calculate some interesting geodesic. That is, geodesic is this path between 2 points on a surface. This is the path of shortest distance between 2 points on a surface. When the surface is a plane surface, we see that the shortest distance connecting to each point is a straight line, but this is not true when the surface is a curved one, and the path of shortest distance is called a geodesic, and geodesic plays an very important role in general theory of relativity. In the next class, we shall calculate few very simple geodesics.